Okay. So, in the last class we are discussing about the binary subtraction using 1's complement and 2's complement methods. Okay. So, in that most of the processors uses signed 2's complement method, because so if any intermediate overflows are present, then we can simply neglect those. Okay. So, today we will discuss about the architecture or circuit diagram of this binary subtraction using 2's complement method. So, as we have discussed, so in binary subtraction using 2's complement method, so if you want to perform say 1000 1001 minus 1000, so we have to take minute as it is 1001, subtract, we have to take the 2's complement of this. So, the 2's complement of 1000 is 1's complement is 0 1 1 1 and 2's complement will have to add 1. So, 1 0 1 0 1 0 1 is same. 2's complement and the original number both are same in this particular case. So, now the subtraction will convert into addition. We perform this addition bit by bit 1 0 0, this is 1 0, this is called end around carry. You can also call as a overflow. So, if end around carry occurs, then you have to neglect it and result is positive. So, this itself is result, this is result as is. So, on the other hand, if we have 1000 minus 1001, you have to take the subtrahend minute as it is, subtrahend you have to take the 2's complement. So, the 2's complement of 1001 will be 0 1 1 0 is 1's complement, you have to add 1. So, 0 1 1 1, you have to add 1 0 1 1 1. So, you will get 1 1 1 1, no end around carry. So, it says that the result is negative, result is obtained by taking the 2's complement. So, what is 2's complement of 1 1 1 1? 0 0 0 0 is the 1's complement, 2's complement becomes 0 0 0 1. So, this is 2's complement of 0 0 0 1, this is the result. Now, how to implement this algorithm using digital circuit, or what is the architecture correspond to this examples. So, in one case in subtraction you have to take the complement of 2's complement of subtrahend. Okay. So, for that, so we need a 4-bit triple carry adder that we have discussed in the last class. This is 4-bit triple carry adder. This will have two sets of the numbers. If I assume that these numbers are in general, I want to perform A3, A2, A1, A0 minus B3, B2, B1, B0. Then I have to take to implement this using addition. I will take this as it is, I will take the 2's complement of this one and will perform the addition. Okay. So, I will take A3, A2, A1, A0 as it is. Then I will take B3, B2, B1, B0 through NOT gates. So, this will give 1's complement if I pass through the NOT gates. This is B3, B2, B1, B0. But what is required is 2's complement. So, this has to be added, these two set of the numbers has to be added. So, we make this C in as 1, so that we will get 2's complement. If this is 0, 1's complement, if this is 1, 2's complement. Then I have got the minuend as it is, and subtrahend we have taken the 2's complement of subtrahend by adding 1. Okay. Now, after adding this, so you will get 2 conditions. This we can call as C out, see end around carry. So, end around carry can be either 0 or 1. So, if end around carry is 0, you have to take the 1's complement of this sum. So, you will get sum here. You have to take the 2's complement of this sum. If end around carry is 1, then simply you have to neglect this end around carry, result is as it is, whatever the result that you have obtained here is the correct result. This result you have to take as it is. If C out is equal to 1, and you have to take the 2's complement if C out is 0. So, how to implement this logic? I will put this somewhat wider. Okay. So, before going for this implementation of this logic, I will just give a simple circuit exclusive OR gate. Okay. So, if I take exclusive OR gate, if one input is x, other input is 0, what will be the output? So, this is x into 0 bar plus x bar into 0. So, this is nothing but x. So, on the other hand, if I take one input as x, other input as 1, then what will be the output? X into 1 bar plus x bar into 1. So, this is nothing but x bar. That is, for the exclusive OR gate, if one input is 0, the output will be same as the other input, and similarly if one input is 1, the output is complement of the second input. Okay. That logic we have to play here. So, you have to take 4 exclusive OR gates, because in one case I want the result as it is, in the other case I want the complement of the result. So, that can be implemented by using this exclusive OR gates. So, one input will be the sum output that will be obtained from this 4 bit ripple carry adder. Okay. So, what about the other signal? This is the final result. If I call this final result as S3, S2, S1, S0, subtraction result. So, this is S3, S2, S1, S0. But what will be the second signal? So, this C out we have to use. So, if C out is 1, I have to take result as it is, but if one input is there, normally for exclusive OR gate we will get complement. So, you have to pass through this C out through the NOT gate. So, that whenever C out is equal to 1, this is 0. So, 0 means as it is. So, whenever C is equal to 1, result is as is. Okay. So, this you have to give as a common signal for all the exclusive OR gates as a second input. So, this will perform the 4 bit binary subtraction. This is not yet over. So, this is actually how to take the 2's complement as is, otherwise you have to take the 2's complement. So, with this logic you are getting the 1's complement of this. This is not the final result. Okay. So, if C out is equal to 1, then this will be 0, you will get as it is values. If C out is 0, you will get the complement of these values. If I assume that this is some P3, P2, P1, P0. So, the output here will be P3, P2, P1, P0 if C out is equal to 1, because if C out is equal to 1, this C out is equal to 1, this is 0. So, the other input is 0 means the same P3, P2, P1, P0 will be the output, and if C out is 0, this will be P3 bar, P2 bar, P1 bar, P naught bar. But how to get the result? You have to take the 2's complement. This is only 1's complement only. So, we need to connect one more 4-bit triple carry adder here. So, one set of the inputs are this one. If I call this one as Q3, Q2, Q1, Q0. So, this Q3, Q2, Q1, K0 can be either P3, P2, P1, P0 or complement of that depends upon the C out. Now, I have to use another 4-bit triple carry adder. This is just to add 1 or to add 0. Okay. So, this if I call as C in of this one, this is C in of the first adder. If I call as this as C in dash. So, to get the 2's complement, whenever this P3, P2, P1, P0 comes as a bar, that is when C out is equal to 0. When C out is equal to 0, this should be 1, if C out is equal to 0. Because C out is equal to 0, we need the 2's complement. 1's complement I have obtained by using these exclusive OR gates, and to get the 2's complement I have to add 1. Of course, I will give the second set of these signals as permanently 0. This I will apply as Q3 is over R3, R2, R1, R0. If I assume, so this actually I will connect to all to 0. So, this I will ground all. I will ground all these signals. So, that if C dash is equal to 1, 1 will be added to Q3, Q2, Q1, Q0. If C in dash is 0, 0 will be added to Q3, Q2, Q1, Q0. So, what will be the C in dash now? So, if C out is equal to 0, I have to add 1. If C out is equal to 1, I have to add 0. Okay. That same logic you can obtain here. So, if C out is equal to 1 here, so this output will be 0. So, C out is equal to 1 means this is 0. So, that is what I want. If C out is equal to 1, so I have to add 0. So, this directly I can connect this C out signal to this C in. This is nothing but C out bar. So, whatever the C out bar that we are going to obtain here, we have to connect here. So, that when C out is equal to 0, C out bar is 1. So, 1 will be added. When C out is 1, C out bar becomes 0. So, 0 will be added. So, C in dash is simply C out bar. Okay. Then here we will get the final sum outputs. This is S3, S2, S1, S0. We will get some C out dash say. This we are going to neglect. This is how we can perform the binary subtraction using 2's complement method. Okay. So, I will not write the Verilog code, because in most of these processors we will not have this binary subtraction circuitry separately. Instead, we have only one circuit which is capable of performing both addition as well as subtraction. Okay. That circuit we will call as adder oblique subtractor, because most of the modules are common. So, instead of using individual modules for the adder and subtractor, so we can play some logic where we can combine these two into a single block by sharing the common resources. That is the idea behind this adder subtraction. So, we are going to share the common resources. So, I will just discuss about this adder subtractor, then I will write a Verilog code corresponding to the adder subtractor by instantiating these 4-bit triple carry adders, because in the earlier lecture, so we have discussed how to construct, how to write the Verilog code for corresponding to 4-bit RCA, okay, using full adders, then full adder using half adder and so on. Okay. Now, what is the modification that we have to do here? So, now we will consider 4-bit binary adder oblique subtractor. So, I have similar sort of the circuit. I will draw here the similar sort of the circuit. So, we require two 4-bit triple carry adders. This is one 4-bit triple carry adder. I will call this one as module M1, and I require one more 4-bit triple carry adder. M2. Okay. So, each triple carry adder will be having two sets of the inputs. This is one set of input, this is another set of input, and then we have one carry in, one carry out, then 4 sum bits. This is the structure of a 4-bit triple carry adder. Here also we will be having two sets of the inputs. This is one set, this is another set, and then you will get 4 outputs. Then this is C out. Now, how to interconnect these two 4-bit RCS? Okay. Again we will come back to this example, like if it is addition, if this is 1000 plus 1001, then simply you have to add bit by bit 100 and this is 10. So, this along with this 1, this is the final result along with the carry. Even if it is 1001 plus 1000 also same answer 10010, this is the final result. Whereas, in case of subtraction, as I have already discussed, so this 1000 minus, if you want to perform 1001, you have to take 1000 as it is, and you have to take the 2's complement of this one and you have to add. So, this 2's complement of this one is 0111. So, we will get 1111. So, no end around carry. So, you have to take the again 2's complement of this to get the final result, which is 0001 is the result. Whereas, here if you want to perform 1001 minus 1000, this you have to take as it is, this you have to take the 2's complement, also same thing, we have to add, then 10001 end around carry. So, this as it is the result. How to implement this logic is, now I have to use an extra control signal, M is another control signal such that M is equal to 0, this is the M is the control signal. So, I am going to use a M control signal such that M is equal to 0, this circuit will act as a adder. If M is equal to 1, the same circuit will act as a subtractor. You can design in the other way also, it is up to you. M is equal to 0 for the subtraction, M is equal to 1 for the addition. You can design in that way also. So, here I am taking this M signal here. Now, I am taking in general, this is I have to perform A3, A2, A1, A0 plus or minus B3, B2, B1, B0, and finally, I want this result as S3, S2, S1, S0. So, this can be either addition of these two numbers or subtraction of these two numbers. Okay. So, in any case if it is addition or subtraction, this I have to take as it is, A3, A2, A1, A0 as it is we have to apply to the 4 bit triple carry adder. So, I will take this input as A3, A2, A1, A0. Whereas, this second number we have to anyhow perform the addition, either we have to take the direct B3, B2, B1, B0 or the 2's complement of this, that depends upon the m. If m is equal to 0, I have to take the direct numbers, if m is equal to 1, I have to take the 2's complement of this number. So, here this number will be direct B3, B2, B1, B0 if addition is nothing but m is equal to 0, and this should be B3 bar, B2 bar, B1 bar, B0 bar plus 1, that is 2's complement if m is equal to 1. So, how to derive the logic correspond to this? As I already discussed in the earlier binary subtraction, exclusive OR gate will perform this type of operations. Okay. So, I will take here B3, B2, B1, B0, I will take exclusive OR gates. So, I will give one signal as this m signal, so if m is equal to 0, I have to keep as it is. I know that for exclusive OR gate, if one input is 0, the other input will be the output. Okay. This I am going to apply here, this B3, B2, B1, B0. So, if m is equal to 0, the same B3, B2, B1, B0 will be available here. If m is equal to 1, B3 bar, B2 bar, B1 bar, B0 bar will be available, that is 1's complement, but we want the 2's complement. So, what we will do is m is equal to 1, I want the, if m is equal to 1, I need the 2's complement. Okay. So, the same m we can connect to here. Clear? So, m is equal to 1. So, here it will give the complement of these values here, at the same time it will add 1 also. So, that you will get the 2's complement of this B3, B2, B1, B0 will be added to A3, A2, A1, A0. Okay. Till now we have obtained either sum of these two or sum of this plus 2's complement of this. Now, the actual logic appears here, depends upon the C out. So, there are 4 possible conditions. So, okay, this intermediate result is a final result in some cases, and this intermediate result, so 2's complement will be the final result in other case. Okay. If I call this intermediate result as Q3, Q2, Q1, Q0, and final result is S3, S2, S1, S0. This Q3, Q2, Q1, Q0 should be equal to S3, S2, S1, S0, in which cases if this is addition and if it addition also you have to be equal, in subtraction also if there is end around carry, subtraction with end around carry. This will be equal to S3, S2, S3, S2, S1, S0 is equal to 2's complement of Q3, Q2, Q1, Q0, in only one case where in subtraction without end around carry. How to implement this logic? Okay. In 3 cases this output is the final output, in only one case the 2's complement of this one will be the final output. Okay. So, for that I am using a simple logic here. Okay. So, M is going to decide whether it is a addition or subtraction, and this C out is going to decide enter one carry is present or not. So, anyhow I have to use the exclusive OR gates here, because I have to take the 2's complement in one case. So, I will give this exclusive OR gates. I will give the exclusive OR gates. This is third exclusive OR gate. This is fourth exclusive OR gate. So, in 3 cases, as I have told, the same input has to be transferred to the output. In only one case the complements has to be taken, at the same time this also have to make as 1, so that it will be 2's complement. Okay. So, if I assume that the signal that we are going to connect the common signal as this common signal, if I assume this common signal as say some Q, capital Q. Okay. So, if I would put this capital Q, if M is 0, what does it means? Addition. In addition, regardless of whether you get this carry or not, I am going to take this Q3, Q2, Q1, Q0 as the outputs, no need to take the complement. So, regardless of the carry can be 0 or carry can be 1, this is for addition. So, as it is you have to take means Q should be 0. If one input to this exclusive OR gate is 0, then as it is this Q3, Q2, Q1, Q0 will be appeared at the output of the exclusive OR gates. So, in addition, regardless of this C out, I have to take the direct output. If this is 1, so this represents subtraction. So, in subtraction also in one case I have to take as it is, in the other case you have to take the 2's complement. So, what is that case? If carry out is, so you see here, if there is no carry out you have to take the 2's complement. So, if carry out is 0, you have to take the 2's complement. 2's complement will be obtained by taking Q is equal to 1 as one input for the exclusive OR gate, so that 1's complement will be obtained, at the same time you have to add 1 also. So, in fact, this Q has to be applied to both this one input of the 4 exclusive OR gates as well as the C in dash or C in of the second carry look ahead adder. Okay. This should be same as Q, because whenever you want to take the complement of this Q3, Q2, Q1, Q0, that is 1's complement, at the same time you have to add 1, so that you will get 2's complement. If this is 1 means there is under 1 carry, so result will be as it is. So, this Q is equal to 0. So, what is the Boolean expression for Q now? Using this logic, you can easily write down the Boolean expression for Q. Therefore, Q is equal to, only one min term is there. So, this is M C out bar. So, simply Q can be obtained using this M signal. This M signal is one input, and C out you have to take through NOT gate, you obtain through the AND gate. This output has to be given as a Q. This is Q signal. So, this Q signal will be the input of the 4 exclusive OR gate, one input of the 4 exclusive OR gate, and at the same time the C in. Okay. So, this logic will play. Okay. So, and what about this second set of the inputs? This should be all grounded, so that this circuit will add only, either this will add 0 0 0 1 or 0 0 0 0, means as it is this data will be transferred. Okay. And this C out will be useful, this final C out you can call as C out double dash. or C out dash simply. This will be this C out dash in case of addition, this there is a fifth bit. So, this along with this bit and these 4 bits is the final result in case of addition. Okay. Otherwise, in case of subtraction, you simply have to neglect. This has to be neglected in subtraction, and in addition this is the fifth bit of the result. Okay. So, this is the logic circuitry. Okay. So, these are the final S3, S2, S1, S0. So, this is a 4 bit binary adder oblique subtractor. Okay. So, in the earlier lecture we have discussed about how to construct a full adder using half adder. Initially I have written a Verilog code for the half adder. Then I have discussed how to instantiate 2 half adders along with 1 OR gate to construct the full adder, and using 4 such full adders I have constructed the 4 bit triple carry adder. Now we can even instantiate this 4 bit triple carry adder. The name that I have given is 4 bit underscore triple carry adder. So, 2 such modules you can instantiate with some additional circuitry to implement a binary 4 bit binary adder subtractor. Now, what will be the Verilog code corresponding to this one? So, simply this circuit we are going to map onto the code. So, if I take this block as 4 bit adder subtractor oblique, this is 4 bit AS adder subtractor. Okay. So, what will be the total final signals for this one? So, we have 2 sets of the signals A3, A2, A1, A0, and then one final one input carry, then second set of the inputs B3, B2, B1, B0, then we will get one final C out, we are calling this as C out dash, okay. And then finally we will get S3, S2, S1, S0. This is equivalent to whatever the circuit that we have derived. So, inside that block we have this complete circuitry. Okay. If I assume this as a complete block, these are the 4 set of one input, this is 4 set of another input, okay. And M is also one control signal is there, I will include that M also, M is one additional signal, and the remaining all are this C out, this Q, these things are all internal, okay. This is also internal. So, this is final external C out dash and S3, S2, S1, S0, remaining C in dash, all those things are the internals. We have to define that as a wires. Okay. So, you have one more signal which is called as M signal. I will give one more signal which is M signal. This is going to decide whether this circuit is going to perform addition or subtraction. Okay. So, module. So, overall block is this 4 bit underscore AS adder oblique subtractor. Okay. So, what are the different outputs and inputs of this one? Outputs are S3, S2, S1, S0. This you can represent with the vector, okay. S with the 3 comma 0 is 4 outputs. Another is C out dash is the output, and what are the inputs? We have M, C in, and 2 sets of these inputs, A with 3 comma 0, B with 3 comma 0. This is the initial definition of the inputs and outputs. Okay. Then you can individually write input and output. Output, the final output is S comma 3:0, C out dash. These are the outputs. Inputs M comma C in comma A 3:0, B 3:0. This is how we can represent the arrays. Now we have to define some wires. What are the different wires required? You see here what are the connections that are not available outside is here we require this. Okay. I will call this one as say P3, P2, P1, P0. So, these 4 wires you have to define. Then here we have Q3, Q2, Q1, Q0. Okay. Similarly, here you can call this one as R3, R2, R1, R0. And this C out we have to define as a wire, and after this NOT gate you call this as some T input, this also you have defined as a wire, then Q also another wire. So, what are the different wires? So, this also you have to make as a ground. So, let us take this one as S we have defined, you call this as G3 grounds, G2, G1, G0. So, what are the total wires? I will write here now. So, these 4 sets G, P, Q, R, these are the 4 set of the wires that you have to define. Wire G 3:0, P 3:0, Q 3:0, R 3:0, and then you have C out, output of the NOT gate we have defined as T, and the overall output you have defined as Q. So, what else? This I have already defined, C out, this T and this Q I have defined as the wires, and then this Q is anyhow this C in is Q only. Okay. So, these are the things that you have to define as a wires. Now, we have to instantiate. First we generate this P3, P2, P1, P0 using B3, B2, B1, B0. Okay. So, for that you have to write exclusive OR gates. XOR output of this one is P3, input is M exclusive OR with M comma B3, right. This is P3 is M exclusive OR with B3. Similarly, P2 is M exclusive OR with B2 and so on. Exclusive OR P2 comma M with B2, exclusive OR P1 comma M comma B1, exclusive OR P0 M comma B0. Okay. So, what else operations you have to do? So, you have to generate T, which is NOT gate output. T is the output of the NOT gate, input of this one is C in dash. Is it correct? C out, I think, C out. This is C out, output is T is equal to C out bar. Then Q is equal to this M and with T, and output is Q, inputs are T and M. What else? I have generated these Qs, then I have to generate Rs by exclusive OR with Q and small q's and capital Q. Okay. R3, R2, R1, R0. Exclusive OR R3 is the output, Q is one input, exclusive OR with Q3. Similarly, exclusive OR R2, Q is the one input, Q2 is the other input. Exclusive OR R1, Q and small q1. Exclusive OR R0, Q and small q0. So, this will generate. So, these 4 will be generated R3, R2, R1, R0 by exclusive ORing with this. Okay. So, we have generated this. This C in is anyhow this Q, Okay. Now, this G3, G2, G1, G0 we have to make as 0, that you can do it by using assign. Assign G3 is equal to 0, assign G2 is equal to 0, assign G1 is equal to 0, assign G0 is equal to 0. These are all initialization. Now, the actual program becomes now very simple. We have to instantiate two such ripple carry adders. So, first to instantiate ripple carry adder, RCAs. Here actually for exclusive OR gates you can give some names of these gates also, I have not given here. So, if you want you can give some gate names. Let us just start with say G1, G2, G3, G4, G5, G6, G7, G8, G9, G10. Okay. So, the name that I have given to this RCA in the earlier lecture is 4-bit underscore RCA, and I am calling the first module as M1. So, what are the inputs and outputs of this module? You have to just specify only the inputs and outputs, this input, this input, this input, and then this output, these outputs. Outputs are Q3 to Q0, C out. Inputs are P3 to P0, A3 to A0, and then M. Okay. So, outputs are Q3, C out, comma Q3 to 0, these are the outputs, and inputs are A 3:1, A 3:0 is one set of the inputs. Then the second set of the inputs will be this is P, and then this is, so this is nothing but this M. Okay. So, second set of the inputs is P 3:0 and then M. So, this will perform all the operations that are involved in this. Okay. The outputs are Q3 to Q0. Okay. Now, for the second RCA, if you want to instantiate, so what will be the inputs and outputs? The inputs are R3, R2, R1, R0, this we have already generated using Q3, Q2, Q1, Q0. Okay. And then this is ground, and this one is Q itself. Okay. This Q I have already generated. So, second one is 4-bit underscore RCA M2 block. So, what are the final outputs of this one? Is C out dash is final output, that is the fifth min bit in case of adder. Then we have S3:0 the final result. Then what are the inputs for this one? C in input is, we have Q is the C in input. What are the other inputs? This Q is C in input, other input is R and G. Okay. G's are anyhow 0. Okay. That I have already assigned, R's and G's. R 3:0, G 3:0. So, by just instantiating two such ripple carry adders, we will get a 4-bit adder oblique subtractor. This is over, then end module. So, this is how we can instantiate the lower modules to construct the higher modules. Okay. So, we have discussed about the adder subtractor as a common block. So, if I take this ALU, because the most of the digital computer, what are the various blocks? We have this input block, which is such as the keyboard and mask. Okay. And we have something like arithmetic logic unit, and then we need some control unit, then you need some memory. This is the overall any processor architecture, memory. Then we need some output block where you can store the results such as CRT display or LED 7 segment displays. Okay. So, we are discussing about this ALU initially. So, I start with the basic operations such as arithmetic and logical operations. This will perform arithmetic and logical operations. So, in arithmetic operations basically addition, subtraction, so that I have included in a single block that I have discussed. Now, it can perform the multiplication also, comparison. Okay. So, these are the different operations that will be performed. I will discuss some of the operations. Similarly, in the logical we can have shift, rotate operations and all. And coming for this control unit, you have something like multiplexers, decoders, encoders, these are all will be included in control unit, and you have some flip flops, counters. Okay. So, I will discuss some of these examples of these control units and some examples for these arithmetic and logical operations. Okay. So, the next operation is, we have discussed the addition, subtraction, the next operation is multiplication. Okay. I will just start with a simple multiplication algorithm, binary multiplier. Suppose if I want to perform 2 bit by 2 bit. So, we have A1 A0 is one say input, B1 B0 is another input. So, this normally conventional like conventional decimal multiplication, you have to multiply A0 with B0, A0 with B1, A1 with B0, A1 with B1. So, this is B0 A0 is the first bit, B1 A0 is the second bit. Now, with A1 B0 A1, B1 A1, we have to finally add. So, how to implement this? This B0 A0 means simply AND gate. Okay. So, you take two AND gates, one input is common which is A0 here. Okay. You give this A0 as one input, this is A0. Two possibilities are, you have to give B0 and at another place you have to give B1. So, these two terms will be generated. This as it is the final result. If I call this output as C0, C1, C2, we can add one more bit also, because 2 bit by 2 bit multiplication, what are the highest number of outputs that can be available? 1 1 into 1 1, 3 into 3 in decimal, this is in binary, 3 into 3 in decimal, which is equal to 9. To represent 9 we require 1 0 0 1. So, outputs are 4. So, C3, C2, C1, C0. So, this is simply C0, and to get C1, so you have to take one more domain set of the gates. So, you take A1 as the another input. So, this will generate, this will give as B0, this will give as B1, these two terms will be generated by this. Okay. So, what you have to do now? B1 A0 is here, B1 A0, you have to add to B0 A1, this is B0 A1. These two you have to apply to the half adder, because only 2 bits half adder is enough. So, by adding these 2 bits you may get one some bit is C1, some bit is C1, carry bit you have to add along with B1 A1. So, the carry of this one, this is some bit and this is carry bit. So, this you have to add to another half adder whose second bit is A1 B1. This is another half adder. So, the sum bit will be C2, C2 will be sum bit and carry bit will be C3. This is how you can perform a 2 bit by 2 bit multiplier. So, if I increase the number of bits, then we have to use ripple carry adders again. So, I can construct the larger multipliers using ripple carry adders, so that I can instantiate this ripple carry adder only to implement a larger multipliers also. That we will discuss in the next lecture. Thank you.